let's now start about regularization. And maybe rather than throwing a definition of you how to define which regression or lasso, I will try to kind of motivate it step by step and show how it can be kind of at least intuitively be related to the subset selection we did right now. So let's just recall from the first lecture where we did linear regression, that kind of in linear regression we were looking at a optimization problem. So we want to minimize a function, we want to minimize a loss function here. So this would be, this would be our loss, which is the least squares loss, and we want to minimize it over all the parameters a, where a are the coefficients which are inside of this function. So we have f of x, which is just a0 plus a1 x1 plus and so on ap xp. So the dependence on a is within f. Sometimes I might just put a little subindex a as well to clarify it, but you know that the a dependence is through f. So this is a kind of optimization problem I want to solve, and it might make sense to think maybe, well, how would the subset selection look like in this context? What would change in the optimization problem, and how is that maybe a more complicated optimization problem? How can we make it simpler? So that's something I wanted to discuss with you right now. So let's just look at the loss function. So we kind of want to, right now we want to minimize overall a, the least squares loss. So we have yi minus f of xi squared basically, and then summed over all I. And so this is the loss function here, exactly what we had on the previous sheet. And for example, what happens if we do subset selection? What happens there? So all that happens is that if you look at this expression we had for fx, where I had a0, and we will kind of ignore this a0 for a bit. Let's just focus on the coefficients which come with the predictor a1 times x1 plus a2 times x2 plus a3 times x3 plus and so on ap times xp. I just written out a few of them because what happens if, for example, if I say I have subset selection and I say I want to look at a model where I have p minus 1 predictors, for example, I will look for the one. If I do backward subset selection, I will look which predictor will I exclude. But just to let you know, excluding a predictor is exactly the same as setting a to 0. If I set a to 0, I exclude the predictors there. So effectively, excluding predictors means just setting some of the a's to 0. So if I wanted to have a subset selection where I remove 3 predictors, all I'm doing is basically constraining my optimization to the condition that 3 of the a's must be 0. And this is just what subset selection does. So I can kind of write it. I could write it out in words. For example, I could say I want to minimize the loss function over a subject to the condition that, say, only m predictors are non-zero. This is one way of writing it. This is kind of a valid form of writing the optimization problem of, this would be even full subset selection, where I subject to the condition that m predictors are non-zero. So I have to basically, to solve the optimization, I would have to go over all kind of partitionings and figure out which of the p predictors, which subset of m is the one which gives me the best loss function. This will be the minimum, the one I'm looking for. But obviously you see this is even a bit tricky to write this down, and I wrote it down as a sentence, but how am I going to teach it to the computer? The only way is again to go back to running through all the different subsets, and that's not very useful. But another way I could look at it is say, well, actually, what does it result in if I set sum of the a's to 0? It means that overall the magnitude of all a's is somehow decreasing. So if I look at and I say the magnitude, because obviously the a's can be positive or negative, but if they are 0, the magnitude would be smaller, and you know that, well, you already saw with the loss function, we do not like magnitude, we prefer squared. But for example, if I know that if I take all the AIs and I square them and I sum over them, ignoring the A0, so all from 1 to P, then obviously if I do subset selection, I will set some of them to 0, and this sum would be necessarily smaller. But I don't know exactly how small it would be, but kind of intuitively, this could lead us to another way of saying, how could I potentially do this, this form of controlling the predictors is by saying, well, maybe one way of kind of taming the model would be to just say, I want to just constrain this sum to be smaller than a certain value, which is quite similar to the effect of actually setting some of them 0. So actually setting some of them 0 will also have the effect that it will reduce this sum. Now, reducing the sum doesn't set some of them to 0. This is one of the issues here, and this is something we want to solve later. But at least it's a valid attempt for kind of controlling the complexity of the model. I might not set it to 0, but if I set this value here to, rather than setting it to 0, I could set it to 0.001 or a tiny number. This might already in practice be good enough. So all I really want to assure that this sum is not too big. And I can just say, what if it's smaller than some constant c? And this is this is the way how I would like to phrase it. So I'm looking at the optimization problem where I want to minimize my loss function, sum over I yi minus f of xi squared, subject to the condition that the sum over all the coefficients I'm optimizing over is less or equal to some constant or some budget, you might call it. I have an overall budget of coefficients, and I kind of control this to be small. This will eventually set some of the a's to be something very tiny, because otherwise I would be exceeding my budget, and this is a very similar effect to setting them to 0. Obviously, it doesn't help me so well with interpretation because I do not know exactly who is 0, but making them small at least has the same effect on the error on my cross-validation. So this is actually the formulation of regularization I'm after, and this is called also ridge regression. And yeah, sorry, sometimes the slides say rigid regression, should really be ridge regression. Somehow the spelling checker messed that up. But this is called ridge regression. Some people also like to call it Tikhonov regularization, which is another way of formulating this problem here. So this is basically the formulation, but this is not necessarily the most useful formulation. And to phrase it in a more useful formulation, we have to know a little bit about optimization. So you might not be too familiar with the theory of optimization, but this thing is called a constraint optimization problem, because I have my objective function, I want to minimize the loss, and I have the second term. So this term here is called the constraint. And I have to minimize the loss function subject to the constraint. Now, constraint optimization is more complicated kind of numerically to do it. So people like unconstrained optimization because it's easier. And there are ways mathematically to transform this problem into an unconstrained optimization problem. Now, if you have heard what a Lagrange multiplier is, this should hopefully ring a bell and you can see, oh, now I know how it works. But if you haven't heard about Lagrange multiplier, it might be a bit of a stretch to see the relationship, but I can at least intuitively tell to you that you can effectively transform any optimization problem into a related optimization problem, any constrained one, which is called the dual optimization problem, which is unconstrained. And the way to write it is, if I write minimum of A, now I have the loss function, and then I write plus lambda times this expression, sum of 1 till p of ai squared. Now this is called the dual optimization problem, dual to the one above, dual to the constraints one. The nice thing is that now it's unconstrained, it's just a single optimization, a single minimization here. Now you see those terms are obviously related. I have the quadratic term, which is obviously related to the other quadratic term above there, and it's dual in the sense that c and lambda are related. So I have c here, sorry. So this optimization, this quadratic term here is obviously related to this quadratic term here, and this constant c here is related to this lambda. And basically what happens is c is inversely related to lambda. So, and this is not exactly precise, I mean, don't read it as an equation, but effectively large c has the same effect as small lambda, and there's a lot of math behind it, but at least I want you to have an intuitive understanding of why that's the case. So what happens if I take c to infinity? Obviously c to infinity means I have no budget constraints. A can be anything. That's effectively the same as ignoring the constraints up here. The same as if c is infinity, I could just delete this because effectively this constraint just is irrelevant if c is infinity, which is exactly the same as here. I would set this constraint equal to 0. If I set lambda equal to 0, the second term is gone. So then I also got rid of the constraint. So here you can already see that c going to infinity means no budget, which is the same as lambda being equal to 0. And it's also clear that, for example, if c is very large but not infinity, then the constraint is less relevant. I have a very big budget, so I don't really care so much about the budget. And here it means small lambda. So a small lambda corresponds to a big C, and small lambda effectively means the same as saying that the second term is less relevant. So the optimization problem is dominated by the first term here. Now the kind of opposite expression would be if I would set c equal to 0. If I would set c equal to 0, then effectively all my AIs would have to be 0, because that's the only way how I can fulfill the constraint. And this will correspond to the limit where lambda will go to infinity, because if lambda will go to infinity, then the minimization problem is dominated by the second term below here. If this term goes to infinity, this whole minimization problem will be dominated by this term, because the first term here will basically be irrelevant with regard to the second term. So I will also get minimize the sum over the AI squareds, and the solution to this minimization problem will just be all AIs equal to 0. So I can see at least the limiting cases that large C, or that kind of infinite C, corresponds to lambda equal to 0, and c equal to 0 corresponds to lambda equal to infinity. And again, this is just an intuitive picture, but you can read about optimization problems and about the dual optimization problems if you like a little bit more of the math. Now, if you're a physicist, you might have seen those duality relationships as well. For example, in physics, for example, volume and temperature are dual variables basically. For example, I can have a cup, I can fix a lid, now I have a fixed volume, but pressure can vary. Or I can put a stone on the lid, in which case I have a fixed pressure, but volume can vary. But for each pressure, there's a kind of corresponding volume, exactly as here for each lambda, there's a corresponding C. Now, I know some of you are also coming from an economics background, so probably you've seen a lot of this Lagrange multipliers, because they are quite commonly used in economics as well to solve certain optimization problems. So hopefully you can relate it somewhat to what you saw in the past. So kind of to come back to the next slide. So what we have seen so far is that I can basically extend my my optimization, my regression problem to something which is called, well, it's called rich regression, by introducing this penalty term. So rather than looking at the normal optimization problem, this is exactly what I solve in linear regression, I now add this constraint. So subject to the condition that the sum over those AI squared is less than some budget. Now we have also seen that there's a dual version of this optimization problem, and at least in the dual version it's much nicer, because now I can write it as a single optimization problem. It's a single minimization about two terms. The first one is the loss function, and the second one is called the penalty term. And the penalty term depends on this parameter lambda, which is called the shrinkage parameter. And this structure is a very generic structure. You will see that whatever fancy machine learning model we will do later, it will always decompose into some optimization over something which is loss function plus shrinkage times penalty. It will always have this form here. And this is something very useful to keep in mind. And the nice thing is that effectively now lambda is something I can control continuously. And by controlling it, I can choose the flexibility of the model. When I choose lambda very big, it will be the same as a small budget. I will have very small coefficients in the sum, in the total, which means effectively that it's kind of equivalent to if I do subset selection with very few predictors. Now, if I choose lambda very small, which would correspondingly mean C very big, I'm basically having the equivalent to having more predictors in subset selection. But rather than having to explicitly look at all these predictors, I can now basically just tune this parameter lambda continuously, and I can kind of explore the space in complexity, and I can do this Bayes variance trade-off by just kind of tuning the parameter C here. C means more flexible, and I can kind of explore the test error. And I also know that C is proportional to 1 over lambda, so I can also vary lambda, and as I vary lambda, I can kind of move along this axis of flexibility. And one little comment on numerical computation. So obviously this minimization problem we can solve numerically, and we can actually see in a second how we can solve it analytically as well. But the only thing I wanted to point out, so we've already seen when we talked about linear regression, that this term here is a convex optimization problem because it's quadratic. But the second term is also quadratic. So the whole optimization problem is convex. This makes it a very simple optimization problem. As before, it's effectively just having a kind of parabola shape where I want to find the minimum, and I know that there is a unique global minimum and it's easy to find it. So nothing has changed there in terms of complexity, and we can actually see that the analytical solution of this problem is quite simple as well, and I can obtain it rather easily. So here's just one example of how that looks in practice. So before we saw the problem of, so before we did the same analysis on the same data but using best subset selection, now flexibility kind of, the model becomes more complex, more flexible as I go to the right. Now, if I look at the same situation now using shrinkage, then obviously here I am increasing lambda, and sorry, this should be the other way around here. So as I increase lambda, so lambda bigger means C smaller and means less flexibility. So complexity actually becomes bigger as I move to the left, because to the left there's smaller lambda, and smaller lambda means more flexible models. So as I go along here, I will kind of start with some lambda here around 1, and I will start decreasing it, and as I decrease it, the flexibility of my model will increase, and I could see here the error has dropped quite a lot, and I might choose this value of lambda as my optimal value. So it kind of works in the same way as before, but now I can have a continuous variable lambda to kind of go over my my space of complex, or my level of complexity of the model. That's much easier than kind of trying to do the subset selection. All I have to do is vary this parameter lambda. You can do it over a grid. You see here I use discrete values. You can do a grid search, for example, start with a grid of values and start varying them as you go along. And yes, some few remarks on the ridge regression. So I think some we already commented on. So it has a general structure of a loss term and a penalty term. I also mentioned that this problem happened to be convex as well, so we can use standard techniques such as gradient descent. So there's nothing really different in terms of the numerical solution. It works the same as for the unconstrained problem without penalty term. So nothing has really changed. It's not like the problem is more complex than before. And I also mentioned that this dual problem, which is also sometimes called the soft constraint, the one where I have an actual constraint like the sum being less or equal than C, that's sometimes also called the hard constraint. So the soft constraint problem is easier to solve than the hard one, which is in terms of C. And also I've seen the relationship between lambda and C, where I know that that lambda equal to 0 is effectively equivalent to having no C. So it's the original model of linear regression, and if I set lambda being to infinity, it effectively means like I get rid of all coefficients. I will just fit an intercept there. And this is basically all I wanted to say about ridge regression. And now we move into the lasso, and the lasso comes about because actually one issue with this formulation is that it's good in terms of cross-validation. I can nicely control the flexibility of the model, but it's not so good in terms of interpretation. But because actually, while it makes some of the coefficients being small, I can't really say which one is important and which one is not important. It is not like in cross-validation where I would be kind of like in subset selection, where I would be throwing out some of the parameters. I know the model removed those parameters and it only kept those 3 other predictors. So now those 3 predictors are the important ones. Here I can't really say. All it does, it makes those coefficients small. So some of the A's might be shrunken by the regularization to be very tiny, but it's different for me to say whether tiny means really unimportant, because obviously those xi's do have a scale. For example, if xi is GDP, whatever, in $1 trillion, then AI can be very tiny. But if I'm trying to predict my household income, even a tiny a will have an important impact. So just the scale of A doesn't really tell me how important it is. So it shrinks the values, but I don't really have interpretability. What I would really like to have is that some of the A's which are irrelevant will be taken exactly to 0. But this is what we don't get right now. And this is something we will see actually when we move to the lasso, which is what we will do next.